All right, so we are welcome back to Calc 3. We are starting the final chapter, and in some ways, this is a lot of people consider this chapter to be sort of the culmination of everything that we've done in calculus, because it takes a lot of different things that we've done. For if you're in 230, then this is going to rope in everything that we've done in 230 up until this point. If you're in 232, well, a lot of the stuff you should have seen before. Well, you should have seen everything in 231 from before, your multivariable differentiation and things like that. But we're taking those ideas of integration and we're sort of bringing them into a new context. That's what the point of chapter 16 is looking at, other really powerful different things you can do with integration. And in particular, we're going to be integrating a different kind of object. So far, there are lots of different functions that we've looked at and that we've considered over the course of this entire semester. And usually those have been functions of one, two, or three variables, which we usually write as f of x and y, or f of x, y, and z. And we've also considered vector functions. These are functions r of t. They give us a real number, we feed r of t a real number, and it gives us some other number of numbers, usually a vector of 2 or 3 dimensions. So the point here is these are functions where you plug in a number and you get back some number of numbers, or you plug in some number of numbers and you get back a number. But what if you wanted to find a way of plugging into a function 2 numbers and getting back 2 numbers? That's what a vector field is. So a vector field in 2 dimensions is given by some vector of 2 real valued functions, p and q. So you write that as f of x and y is equal to pxy comma qxy. So you feed it 2 numbers and it gives you a vector. Or in other words, you feed it 2 numbers, it gives you 2 numbers. A 3-dimensional vector field is the exact same idea, only in that case, you feed it 3 numbers and it gives you back 3 numbers instead of 2 for 2. So that's what a vector field is in either 2 dimensions or in 3 dimensions. And we've seen these kinds of things all the time. So lots of different examples that we can think of. The most famous sort of a visual aid of a vector field that we've seen, and I pretty much guarantee that everyone has seen this at some point, are wind currents and wind patterns. Wind pattern is a giant field of vectors. It's a giant plane that has a whole bunch of vectors on it that show a flow. On the right-hand side in this figure, we see airflow over a cross-section of a wing. So this whole notion of fluid flow and vector calculus, this becomes really important in aerodynamics and anything that involves any kind of fluid motion. Vector fields are super important for anything dealing with fluid motion of any kind, really. And I've kind of just shown how you visualize these things. So when you think of a one variable function, or actually let me rephrase that. When you think of a function that is real valued, it gives you back a number. Usually you think about that as either a curve in space or a surface in 3 dimensions. Now you can think of a vector valued function in 3 dimensions, which takes in a real number, usually write it by t, and that's going to give you some curve sitting inside of 3-dimensional space. But vector fields are a little bit trickier because you can't really visualize it as a curve or a graph. The problem here is that the graph in question is going to be the graph in question would be 4-dimensional, right? You would have 2 variables, x and y. It would give you back 2 variables. That would be 4-dimensional, and that's not going to make very much sense. So instead what we do is we visualize it using arrows. So at every point, you have an arrow that points in the direction of whatever your output is, and that's why we call this a vector field. So let's look at a concrete example of something like this. So here's a vector field. It's the vector field x, y. Xy is equal to, or f of xy is equal to y negative x. So give me a second. So, that's not what I wanted to do. I'm just shifting around my chat windows and everything else. So let's consider that. So let's draw our coordinates. I'm going to try drawing them a little bit more vertically. keyword try. And what's going to happen at each individual point? Well, you can think of, for example, f of, I don't know, let's say 0, 1 is going to be the vector 1, 0. So at 0, 1, we're getting the vector 1, comma 0, which goes in this direction. What about the vector 1, 0? Well, that's going to be the vector 0, negative 1, which is going in this direction. And the vector of 0, negative 1, which is negative 1, 0, going in the opposite direction. And the vector negative 1, 0, which is 0, 1, which is going upwards. And you're beginning to see what this looks like. It's looking kind of like a swirling kind of thing. If you want to talk about f of 1, 1, that would be the vector 1, negative 1, which would be pointing down in this direction. So we're seeing at this point that this vector field, and you can keep on going. What if you want to talk about the vector f of, I don't know, let's say 1, 2. Well, that's going to be 2, negative 1. So if you're up here at the point 1, 2, that's going to be 2, negative 1, which is going down here like that. So over the course of this entire field, we see what the behavior is. What we get is sort of this swirling, rotating thing. This is a vector field of all vectors that are rotating clockwise. That's what this vector field is giving us. So that's how we visualize these kinds of vector fields. That's what these things look like. Now, by the way, plotting vector fields in GeoGebra is kind of difficult. I don't know if there's an easy way of doing that. So, but you can, but there are lots of free applets that you can use, that you can find online for plotting vector fields if you want to start getting used to what some of these things look like. Vector fields are a very common tool and very common analytic object that we look at in any kind of engineering and anything that involves fluid flow. We can even see this right now. We can see how this vector field appears to be sort of curling and swirling around in this way. And when we begin talking about curl and vorticity, then this is going to become very important as time goes on. All right? So questions about any of this stuff, about what vector fields are, how we visualize them? Okay. So stuff. Now, this shouldn't be that alien of a concept in some ways, because we've already seen at least one kind of vector field before. Namely, this is a function where you take in two numbers and it gives you back a vector. And that's the gradient, right? The gradient, which we've denoted by nabla f or del f, takes in two numbers and it gives you back two numbers. Now, in physics, that scalar function is called the potential energy. Okay, strictly speaking, it's the negative of that thing, which is the potential energy. And the vector field is the gradient, is the associated force field. So think back to when we described level curves as sort of contour lines on a map, right? Well, if f is increasing up the mountain, that means that you can think about that as the higher you go, the higher your level curve, the higher f, the bigger f, is more potential energy, right? More potential energy for going downward. But the force is going in the opposite direction, right? The force is going down the mountain. So that's why the scalar function is, it's actually negative f is the potential energy. So, but that's why, and that's why gradients are so important, because they're very significant in the context of physics. We call, and if a vector field is the gradient of a scalar function, then that's called a conservative vector field. A conservative vector field. That's one where the gradient, where the vector field is actually equal to the gradient of a given function. Okay, but here's an important question. Are all vector fields conservative? Are there examples of, let's see. So are there examples of a vector field that are non-conservative? And yes, there are, as it turns out. So if you so is every vector field conservative? And the answer, turns out, is no. And to see why, let's look at the following vector field. I don't know, I'm going to call it fxy. Let's use the same exact one, the same exact one we had before, y negative x. And let's suppose, for example, that you've got some function f of xy has that the gradient of f is equal to y negative x. Well, that means that f sub x, if you differentiate with respect to x, you get y. Okay, well, we anti-differentiate that. That means that f of xy has to be equal to xy plus some other function, which I'm going to call phi of just y. When phi is just purely a function of y, if you anti-differentiate it, right? But on the other hand, if you take fy, well, that's equal to negative x. And that tells you that, that's going to tell you that fxy is equal to negative xy plus some other function, which I'm going to call psi of just x. So what does that tell you? That tells you that xy plus phi y, which again is only a function of y, is equal to negative xy plus psi x. Or to put this another way, psi x, which again is only a function of x, it can only depend on x, is equal to 2xy plus phi y. So the whole point here is that this function psi only depends on x, and this function phi of y only depends on y. And that's not possible. You can't have a function that only depends on x be equal to 2xy plus something that only depends on y. That's not possible. That can't happen. And to make this even more concrete, what if we wanted to take, okay, well, just for completeness and for posterity, what if you take if fxy is equal to xy plus phi y, that means that fy would be equal to x plus phi prime of y. And that's equal to negative x. And that's equal to negative x because that's what the vector field is, which in this case is going to give us that phi prime of y, something that only depends on y, is equal to negative 2x. And that's not possible. Now in 16.3, so tomorrow we're going to look a lot more at these conservative vector fields and see what what some of the other aspects of conservative vector fields are and what makes them so powerful and why they're actually pretty cool and very useful. And if you can find that your vector field is conservative, it turns out you're in a really good spot. And we'll figure out what exactly the details of that are tomorrow. Before we do that, though, are there any questions about anything that's going on so far? So now the other thing I wanted to talk about are things called line integrals. Now, so that's what a vector field is. We can, what can we do with the vector field? Well, like any function, you can differentiate it and you can integrate it. It's funny though, in this particular case, integrating vector fields is a little bit more intuitive in some ways than differentiating them, as it turns out, in terms of what they actually mean. So let's look at that first. how do you differentiate, excuse me, how do you integrate a vector field? And what does that even mean? Well, before we answer that question, we have to look at what are called line integrals. So a line integral, let's recap what integrals we've seen so far. For a single integral, then a single integral that we looked at in Calc 1 and Calc 2, that's just an integral over a line segment. It's the area under the curve, and it's being taken over an interval on the real line. It's one-dimensional. For a double integral, the region of integration, the domain you're integrating over, is a two-dimensional region, which we call D for domain, in the xy plane. And that represents the volume of this object under the surface. And then you get a triple integral. And a triple integral is an integral over the region E, which is just the letter that comes after D, which is the only reason we call it E. And that's a triple integral over a solid region in space. The solid region is sort of a three-dimensional object, and there are three integrals, and it has volume. So these are the different kinds of integrals that we've seen. What's a line integral? A line integral is a different kind of integral altogether. It's an integral that the domain of which is a curve in R2 or in R3. And you may ask yourself, why do we call these line integrals if it's over a curve and not a line? And that is a good question. Curve integral would be a better name for these things. And some authors and some engineers and mathematicians refer to these as path integrals instead of line integrals, because there's absolutely nothing to say that you have to be taking this over a line in the traditional sense of the word. They're just called line integrals for silly historical reasons. And if you want to complain about the nomenclature, I don't blame you, but I was not in the boardroom when that particular decision was made. So I can't really take too much responsibility for that particular decision. You have to take that up with corporate. So, but what exactly are line integrals anyways? How might we interpret these things? And for now, we're going to look at line integrals in the xy plane. The three-dimensional line integrals are calculated in basically the same way, and in some cases interpreted the same way. So there are really two kinds of line integrals that we can talk about. One, you can either integrate scalar functions, or you can integrate vector fields over lines and curves. Let's start off with scalars, because these are a little bit easier. So if you take the integral of fxy ds, that's a scalar line integral, right? fxy is a scalar function. It's a regular old run-of-the-mill two-variable function. What does that thing mean? Well, remember how a regular integral in Calc 1, a regular old Calc 1, Calc 2 integral is just it's just the area under the curve, right? You can think about your integral of f dx is, well, f is just the height of the curve in this case. Well, here it's pretty much the same thing. You can think about fxy as the height of a fence, or the fence or a curtain at the point xy. And if that's how you interpret it, then the integral becomes the total area under that fence. On the other hand, maybe f is the density of some quantity. Maybe that's charge or heat or total number of cars on the road, if you want to talk about discrete objects or things like that. Mass is a very common one, for example. You can talk about the mass density. So if f represents the density of some quantity over this curve, then the integral is the total quantity, right? The total mass, the total charge, the total amount of stuff. That's usually how I think about integrals, is the total amount of stuff, whatever that stuff is. Now the ds in the notation for this line integral is read as with respect to arc length. So, and that should make a certain amount of sense. Remember that we said we used little s to denote arc length all the way back in chapter 13. So a lot of this stuff is going to start coming full circle now. So how do you calculate these things? Well, in order to calculate them, you need to find some way to parameterize the curve. That is, you have to find some vector function r of t. This is not a vector field, by the way. This is just a curve. This is a vector curve in R2 or R3, and it's a parameterization of the curve. So if you have that parameterization, then this is what the formula is. The line integral of your function over the curve is the integral from a to b of f evaluated at r of t times r prime of t dt. So what exactly does this mean? Well, f of r of t, that's relatively straightforward. That's just f of x of t, y of t. So you're translating this from a function of two variables, f of x and y, to a function of one variable, f of r of t. You plug in one number, t, into f of r, and that gives you f of r of t. So that makes sense. That works. And meanwhile, there's this, but that answers what f of r of t is. What about this sort of mysterious, r prime of t object in front of the dt? Why are we saying this is r prime of t dt? Well, that's coming from the fact that ds is r prime t dt. That's what we're saying. We're saying that, that ds, just to remind everyone, ds, that's length, right? That's a small change in length. dt is a small amount of time, and r prime of t in magnitude is speed. So all of this together will give us that speed times time is equal to length. And that's what's going on over here with ds equals r prime t dt. Speed times time is equal to length. And this comes from, this also, by the way, should look similar to what we saw in chapter 13, where ds dt, the change in arc length, ds dt was r prime of t. Right? Now, if f of xy is the constant function 1, if it's a constant, very boring function 1, then this becomes, then you can write this as the integral over c ds. Well, okay, f of r of t is just 1, because f is just 1, so that becomes the integral from a to b of r prime t dt. And you may think to yourself, wait a minute, I've seen that before. I've seen this integral from a to b of r prime t dt. That's arc length. That's the arc length of c. That's exactly right. So I just want to make a comparison here. Remember, if we look back, back in chapter 15, we said that the double integral of the constant function 1 over d, that's the area of d. If you take the triple integral over e of the constant function 1, that's the volume of e, right? The constant, if you, whenever you take the double, triple, or line, single line integral over your domain, and your function, your integrand, is just 1, that's just going to give you the total size, whatever the appropriate size measurement is, area, volume, length, whatever. That's the total size of this object. So in the same vein, the integral over c of the integral over c of the number 1, that's just the length of c. And if you choose to interpret arc length, if you choose to interpret a line integral as mass, the total mass given certain mass density, well, if the mass density is 1 over the course of the entire wire, and you take the total mass, and mass density is just uniformly 1, then the mass is just going to be the length of the wire. So it's the exact same principle as before. Well, we're going to do some examples of this. We're going to do some examples of calculating these line integrals and see what they look like. But before we do that, are there any questions so far? All right. So let's do a concrete example of this. What if we wanted to take the triple integral? Oh, excuse me, not triple integral. Why did I say that? Because I saw the cube and I thought 3. Or whoopsie. So in this case, f of xy. So here, f of xy is xy cubed, and c is given by r of t. R of t is equal to 2 cosine t, 2 sine t, for t between 0 and pi over 2. Great. So now remember now, by the way, just a common strategy, just a general rule of thumb, a very, 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 very useful thing to do is whenever you're going to solve any kind of integration problem, write the formula down first. Always start by just writing the formula down. So in this case, we know that the integral over c of f of xy ds, that's the integral from a to b of f of r of t times magnitude r prime of t dt. Now, in this case, we know what f is and we know what r is. So what's f of r of t? F of r of t. Now, x is 2 cosine, so that becomes 2 cosine t times 2 sine t cubed. Or in other words, this whole thing is going to become 16 cosine t sine cubed of t. Meanwhile, we're going to need to know the magnitude of r prime. For that, we need to know r prime itself, and r prime is going to be negative 2 sine t to cosine t. So the magnitude of r prime of t is going to be square root of 4 sine squared t plus 4 cosine squared t. And under that square root, that's just going to eventually become 2. So the entire object in this case, this whole thing is going to become the integral over c of x y cubed ds. That will be the integral from 0 to pi over 2 of 32 cosine t sine cubed t dt. Now this is just a basic u substitution. This is going to be, in this case, you can re-express this. You can re-express this as the integral from 0 to, integral from 0 to 1 of 16, not 16, I'm sorry, 32 u cubed du, where in this case u is sine of t, and du, in other words, is cosine t dt. So this whole thing is going to become 32u cubed, or in other words, 16u to the 4th from 0 to 1, or in other words, just 16. So the answer to this question is just 16. And that's how we were able to solve it. We were able to just do the regular old u substitution integral without any real difficulty. As a sanity check, this would also be 16 times sine to the 4th of t from t equals 0 to t equals pi over 2, and that would still be equal to 16. All right, so questions so far? Okay. Now, what this means is that there are going to be lots of different parameterizations we're going to have to consider. Now, here are a couple useful ones, and this is an important slide. So, why is the? Oh, sorry, I'm going backwards. One moment. Why is the integration 1/2 u to the 4th and not 1/4? Oh, I made a mistake. Oopsie. Okay, thank you for catching this. I made an error. I made an error in my calculation here. So this should not be 16. This should be, oops. This should be 8. 8 u to the 4th. This is 8, not 16. I thought that seemed a little bit funny at first. Thank you for catching that. So. Yes. Yeah, it should be 8 in that case. So thank you for catching that mistake. I think we're good now, though. All right, so anyways. So some common parameterizations that will be useful for us. If you want to take a line segment starting from R0 and going to R1, the best way to do that is R of t is R0 plus t times R1 minus R0. Notice if you do this, then you plug in t equals 0. you get R naught, t equals 1, that's just going to give you R1. So, so that's a useful parameterization. You can see that it's a line in this case. It's a line that contains, this is a line segment that contains R naught. And it's in the direction of R1 minus R naught. By the way, if you're in 232 especially, or 230, but in particular 232, and you're a little rusty on what on what lines are and thinking about lines and planes, take some time to look back at that, and take some time to look back at formulas for lines and planes, because we are going to be using lines and planes continuously over the course of this, over the course of the last chapter in the class. You can also take integrals. You can also parameterize curves that are functions of x, like y equals is some function of x. In that case, if x is a, then y is just f of a. So the parameterization is just r of t equals t comma ft. And similarly for curves that are functions, x is some function of y, x equals g of y, going from g of t, from t equals a to t equals b. And finally, this gives us the part of the circle that goes from polar angle alpha to beta. And if you're doing a component of a circle, that's r cosine t, r sine of t. Now, can you do r sine t, r cosine t? Yes, you can. You're allowed to do that, but that changes the direction that the curve is going in. In other words, it changes what's called the orientation of the curve. And orientations of these curves is going to be very important for the next thing that we do, which I think is the next slide. So if I remember these slides correctly. But before we do that, so here's an example. So calculate integral over c x cubed ds. C is this part of y equals x cubed between 1, 1 and 2, 8. So in this case, we can say that r of t, now y equals some function of x, right? This is some function. I don't want to call it f because we're going to call the inside integral f. I'm going to call it g. Y equals some function g of x. What that means is that r of t, we can think about this as x comma g of x. In this case, x is going from 1 to 2. Oops, sorry. Yep, I messed up. Now, more specifically, it's not just x g of x. It's actually going to be x comma x cubed. Now, if you really want to be specific about this, now, strictly speaking, I didn't quite write this the way I wanted it to. But what you can say here at this point is r of t is just t comma t cubed. Or you could write r of x is x comma x cubed. It should give you the same answer. The symbol you use, whether it's t or x, it makes absolutely no difference. So you can either use t or x. It doesn't matter. The universe doesn't care what symbol you use. It's a little more traditional to use t. But if you already know that your curve is a function of x, then using x is perfectly fine as well. It doesn't matter what symbol you use. Now, in this case, if x is just t, and that's another thing that I like doing. Whenever and here's another good strategy, or another good practice. Whenever you're writing these parameterizations, another thing you can do is write this as x equals t, y equals t cubed. That's another way of writing this. Now that is the advantage of saying that f of xy, if you want to think about that as f of r of t, that's just f of t comma t cubed. Now in this case, f of xy is just x cubed. So this becomes t cubed. That's not a problem. What about r prime? Well, we're going to need to know r prime of t. Why are we going to need to know r prime of t, by the way? The reason we're going to need to know that, again, writing the formula down, integral over c of f
xy ds, that's the integral from a to b of f of r of t times r prime of t dt. Now r prime of t is going to be 1 comma 3t squared. So the magnitude of r prime of t is 1 plus 9t to the 4th. All of which is to say that the integral from, the integral over c x cubed ds is the integral from 1 to 2 of t cubed, that's f of xy cubed, but evaluated at r of t, times the magnitude, which is 1 plus 9t to the 4th dt. Again, this is a u substitution. Let's see if I can get it right this time. U is 1 plus 9t to the 4th. du is therefore going to be 36 t cubed. So this all is dt. That's 1 over 36. Integral from, after exchanging the bounds, from 10 to 9 times 2 to the 4th is 9 times 16. 9 times that is 72. Times 2 is 144. I think I've done this correctly. Times, now inside of the integral is we're just going to get the square root of u du. So that is going to become 1 over 36 times 2/3 u to the 3 halves from 10 to 144. Or in other words, 18. So it's going to be 1 over 54. 1 over 54 times, trying to use all my tools correctly. 1 over 54 times, I'm just going to write this as 12 cubed minus 10 to the 3 halves. I'm going to leave it at that for now because that's about all that I really care about in terms of what the actual number here is. I mean, if I wanted to, you could write out the whole number, but that's not really the important point. The hard part of all of these is just setting them up. The hard part about doing all of these things is just setting them up and being and knowing what the domain is and what exactly this thing looks like. And by the way, knowing what the domain is for these integrals is half of the battle. Because if you don't know what the domain is, you're pretty much dead on arrival in terms of being able to actually do any of these problems. So make sure that you know what the domain is that you're dealing with as you're going through these. All right, questions so far? Okay. Now, the second type of integral that we'll have to work with is an integral over a vector field instead of a scalar function. Now, this interpretation is a little bit funny. It's not quite a curtain or the total area of a curtain or a fence necessarily. It's the work done by the force field, F. You think about F as a force field. Literally, that's what it's called. Which is just to say it's a field of arrows representing some kind of a force, like gravity or electromagnetism or fluid flow pushing some kind of a particle along a river or something like that. So just a little quick physics note. When I say work, what we mean by that is the work done is, by a force F on a particle moving along some displacement vector d. Well, that's just the dot product of F with d. So in the image on the right-hand side here, if you imagine that you've got some particle moving along d and some force F that's pushing on this particle as it's moving along d, for example, you can think of a motorboat moving along a river. With the motorboat is moving along d, but the current of the river is moving along F.
Well, then the current of the river is doing work equal to F dot D on the boat as the boat is moving along D. Now, why is that significant? Well, if you interpret dr, if you think about dr as a tiny, i.e., quote unquote, infinitesimally small displacement in the direction of r, then you can think of F dot dr as the quote unquote infinite continuous sum of all of the little bits of work that this force F is doing, moving this thing along the curve. So the curve is not a single displacement vector, it's a whole bunch of displacement vectors all strung together to make this nice curve. I'm describing basically a Riemann sum. And the work is just F dot each of those little bits, and then you sum them all up. So that's why we use the notation F, the integral F dot dr for the total work done over the course of this curve. All right. Now, how do you calculate this thing? Well, again, the first step is to parameterize the curve. Now, you don't necessarily need A to be less than B in this case, like we did before, because in this case, you know, the work that you do, the significance in the work that you do is that it has some sign to it, right? The work done is positive if it's going in the same direction as the movement, but it's negative if it's going in the opposite direction. So you can talk about positive and negative work. So you don't necessarily require A to be less than B, but you pick it so that your parameterization of the curve is going along the correct direction. That's what's most important, is that the direction, aka the orientation, is correct. And we also have that dr is r prime of t dt, much as we had before. We can remember, for example, that this is coming from the fact that r prime of t can be written as dr over dt. It's the same principle at play here. Now, if f and r prime are always acute angles, then that means that the work done is kind of in the direction that you're moving in, which means that the work is positive. But if they're obtuse angles, that means that the force is moving in the opposite direction a little bit from the displacement, which means that the answer will be negative. And if they are perpendicular, then the work is 0, or it's a perfect mixture of acute and obtuse, then the net work done is 0. Now the sign is going to be quite important in this case, so let's take a look at what that looks like. So what if you want to find the work done by the force field F xy, which is given by x squared minus xy, and you're going and what work is done here in moving a particle counterclockwise around a quarter circle C of radius 1 in the first quadrant. So you know F of xy, and we know what C is, and it's all drawn over here on the left-hand side. C in this case is going to be given by r of t. Its radius is 1, so it's cosine t I plus sine t j for t going from 0 to pi over 2. And if t is going from 0 to pi over 2, that's going to trace out this quarter circle in this direction. And importantly, this is going counterclockwise in this case, so the directions agree. Notice that the direction that it's going in is going against the flow. It's going against the vector field. Let's see what happens with the work in this case if it's going against the vector field. Well, we know that we know that, again, if you're just writing what the formula is, F dot dr. And by the way, that dot is not negotiable. You have to include that dot there. Otherwise, it doesn't really make sense. So it's the integral from 0 to pi over 2 of f of r of t dotted with r prime of t dt. So we need to know r prime of t, which in this case is negative sine t I plus cosine t j. And f
of r of t, f of r of t is going to be, in this case, sine squared ti minus, or actually plus, I'm sorry, I'm doing this in the wrong way. This x is, because remember what this is saying is that x equals cosine t, y equals sine of t. So this is going to be cosine squared I plus sine t times, actually minus sine t, mess that up, minus sine t cosine tj. So the integral that we're interested in is the integral from 0 to pi over 2 of the dot product, cosine squared ti minus sine t cosine tj, dotted with negative sine ti minus sine t, minus cosine t j dt. Which would be what? Which would be the integral from 0 to pi over 2 of negative sine t cosine squared t plus sine t cosine squared t. And I think that I made a mistake somewhere, because that shouldn't go to 0. So what mistake did I make? Hold on a second. I'm going to pause the recording so I can figure out where I went wrong. I see what my mistake was. My mistake was I made this a negative. I should have made that a positive. That was my issue. So, okay, that fixes it. That fixes it. So this, in other words, should not be negative sine t cosine squared t, or not positive, but it should be negative. So this whole thing, in other words, okay, now I fixed it. 0 to pi over 2. 2 sine squared, sorry, no, 2 sine t, I've had a long day. 2 sine t cosine squared t dt, negative, all of that stuff, because this whole thing's going to be negative. So this, in other words, is going to become 2/3 cosine cubed t, evaluated from 0 to pi over 2, which in this case is negative 2/3. So what does negative work mean in this case? It means that as you're traveling along this curve, you're going against the current. You're going against the grain. If we were to reparameterize this, so we're going in the opposite direction from not 0 to pi over 2, but from pi over 2 to 0, we'd be going in the opposite direction, and we'd be going along the curve. So the fact that we're going against the grain means that this work is going to be negative. Okay, so questions on this example. Okay, so well, here's another instance. What if we want to calculate this integral? Here's fxy is xy squared negative x squared, and c is the curve given by t cubed t squared, going from t equals 0 to t equals 1. Well, again, we just have to remember that this curve, f dot dr, is the integral from a to b of f of r of t dotted with r prime of t dt. And in this case, we're trying to figure out what that thing is. Well, r prime of t is given to us, so r prime of t is quite simple. It's going to be 3t squared, comma 2t. Meanwhile, f of r of t, since x is t cubed, and y is t squared. This whole thing is going to become t to the 7th, because it's t cubed times t to the 4th, negative t to the 6th, negative t cubed squared. So putting all of this together, integral over c of f dot dr is the integral from 0 to 1 of 3t squared I plus 2t j dotted with t to the 7th I minus t to the 6th j dt. This is the integral from 0 to 1 of, in this case, 3t to the 9th minus 2t to the 7th dt. Which, in other words, after doing the integration, which is not very difficult to do in this case at all, 3/10 minus 2/8, just to break everything down completely, or because in other words, this is 6/20 minus, okay, so 1/4 times 5 on both sides minus 5/20. Whole thing becomes 1 over 20. That's pretty much all there is to it. But what I want you to observe is how much, is how useful it is to just write everything down that you know, including formulas, including equations. Because as soon as you write down the equation, that will let you just see, here's everything that I need. I'm going to need f of r of t. I'm going to need r prime of t. I'm going to need these things. And once you write them down, you'll be able to see, okay, this is what needs to happen. This is what I need to figure out. Okay, questions so far? So here's another one. What if we, now you can do this up, there's a typo here, that should be fxyz, I'll fix that. So in this case, our curve is a line segment from 0, 2, 0 to 1 to 3, 1, 4. Remember that we can consider this to be R0 and consider this to be R1. So r of t, we can think as r of 0 plus t times r1 minus r0, which in this case is 0 to 0 plus t times 3, 1, 4. 3 negative 1, 4, excuse me. 3 negative 1, 4. 1 minus 2 is negative 1, not 1. So in other words, this whole thing is going to become 3t, 2 minus t, 4t. So again, we're going to need to, you're just writing down what we need. Integral over c of f dot dr becomes the integral from 0 to 1. Oh, that's the other thing, is I should point out this is t going from 0 to 1 in this case, of f of r of t, that is, dotted with r prime of t dt. Integral from 0 to 1 of, here we go, f of r of c in this case is what? Well, f xy is xy in this case is 3t times 2 minus t, 9t squared, and 3t times 4t squared, or in other words, 3 times 16. So 3 times, and I'll listen to this, 3 times 8 is going to be 24, 3 times 16 is going to be 48, so 48 times t cubed. Dotted with r prime, which is 3, negative 1, 4 dt. I think I got that right. I think I did all my calculations correctly. 0 to 1, integral becomes 9t, 2 minus t, negative 9t squared, 48 times 4, so 48 times 4, 32, 4 times 4 is 16, 192 t cubed. Oh gosh, I'm making a terrible, terrible mistake. What am I doing? Why is so someone should fire me for this offense? You have to add all these things together, obviously, because this is a dot product. You don't get a vector out of this. So after doing out all the algebra, this becomes the integral from 0 to 1 of 18t minus 9t squared minus another 9t squared plus 192 t cubed dt. And after doing all this, because in other words, this, after doing all of this, this is going to become 18, so 9 t squared minus 6t cubed to get negative 18t squared plus 192 divided by 4, which we now know is 48, t to the 4th, evaluated from 0 to 1. 9 minus 6 plus 48, or in other words, just 51. So that's the answer. That's how you work out what these things are. And again, setting it up is usually the hard part. And for that, the most important thing is to know how to parameterize a whole bunch of different kinds of curves, and recognize when those curves are occurring. So questions on this example? Okay. Now there are a couple other ways that Stuart will write this. So if we write the components as, if we write the components of the vector field as fxy equals pxy comma qxy, then you can think of dr as just being the vector of differentials, dr equals dx comma dy. And we write the whole thing as f dot dr equals pq dot dx dy, which just becomes the integral over c of p dx plus q dy, which is a little strange. The book describes p dx and q dy as two different line integrals, separate from the other two that we've already looked at. But we're not really going to discuss these separated integrals very much. We're only going to look at the sum of the integrals as an alternate notion for the integral over c of f dot dr. So in other words, make no mistake. If you see something that looks like some integral of a function times dx plus a function times dy, that's a vector field integral. Even though you don't see any vector notation, that's a vector field integral. It's an alternative way of describing it. So let's look at what that notation can look like. For the first one, if we're saying it's fxy equals x squared I plus xyj, looking at these individually, f dot dr, you could write this as the integral over c of x squared dx minus xy dy. That is a vector field integral. It's the same exact object. It's just another piece of notation. Or if you want to look at the integral over c of fxy, where you've got xy squared negative x squared, this becomes the integral over c of xy squared dx minus x squared dy, same exact story. You can even do it in 3 variables. That doesn't change anything whatsoever. F dot dr is the integral over c of xy dx plus x squared dy plus xz squared dz. It's the same exact principle. And again, even though these look like scalars, even though they're only scalar functions and what appear to be scalar differentials, don't get confused. Those are vector field integrals. Those are absolutely vector field integrals, just written in a slightly different way. Okay, so questions on any of this stuff? Anything we've done so far? If there aren't any questions, then we will we'll end here. Thank you for those who tuned in, and we'll pick this up again tomorrow, looking at some cool things you can do with conservative vector fields. And I'll see you all tomorrow.